Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all to lecture number 42 on the subject of computer organization and assembly language programming. The title of today's session is Functions in Assembly Language, Part 1. This slide shows today's agenda. Okay, first we will have a quick recap on the x86-64 register set, its programming toolchain, and its instruction categories. We will then see the syntax of defining a function and the related call and ret instructions of x86. Well, the main emphasis of today's session will be on the usage of process stack in function calls. Finally, we will understand the requirement of the caller-saved and the callee-saved registers with a sample program as well. Okay, we have a lot to do today, so let's start playing. So let us first have a quick recap. This slide shows the register set of x86-64 microprocessor that of course we have discussed in detail in lecture number 28 of this course. This slide summarizes the x86-64 programming toolchain, the layout of assembly program that we discussed in lecture 29 and 30 of this course. Well, do note the process logical address space, especially the stack at the top, as we will be discussing its usage during the function calls and return. And this slide shows the categories of x86 assembly instructions that we intend covering in this course. And today we will understand the working of these call and ret instructions, which fall under the control transfer category. Well, we have already discussed the unconditional and the conditional jump instructions as well in previous sessions, which are used to change the control flow of program execution to a different address other than the next instruction sequence. Well, dear students, this call instruction is quite similar to the jump instructions, and the difference is that in this call instruction, the return address is also saved on the stack before jumping on to the destination label. Anyway, we will see this in detail in the upcoming slides. Okay, so let me first differentiate between procedure and function and the syntax of defining a procedure in assembly. Well, in computer programming languages, procedure, function, subroutine, or sometimes called a method, is a named piece of code that can be called from a program in order to perform some specific task, thus making a program more structural, easy to understand, and manageable. Well, one of the main difference between a procedure and function in literature is the return statement of a function returns the control as well as the function's result value to the calling program or to the calling function. On the contrary, the return statement of a procedure returns only control to the calling program. Well, we all know that a label is a named memory location in the code section where our program can jump conditionally or unconditionally. In NASM, we can define our function with a label at the start of the function and a ret instruction at the end. So this is how our function is defined in NASM. Well, in some assemblers like the Microsoft assembler MASM, there is a different syntax to define a procedure as shown over here. Note the start of the function, we use the procedure name followed by the proc keyword, and at the end of the function after this ret call, we use the procedure name followed by the end p keyword. Since we are using the net wide assembler, So we will use this simple way of defining a procedure as well as a function. Okay, well, dear students, an assembly procedure is defined as a set of logically related instructions having a name that is meant to be called from different places, that can accept parameters via registers, global memory locations, or stack, that can do some processing, for example, adding numbers, printing strings, getting input, and so on, and that may return some value to its caller via register, global memory location. And the agreement on how to pass the parameters and return values and how to share CPU registers between the caller and the callee is called calling convention. We will discuss the passing of parameters to a function and returning values from function in our next session, inshallah. And today we will see a sample program over here having two functions, namely the main and the foo. The first instruction of the main function is at address 0xf00, and the last instruction is at address 0xf69. Similarly, the first instruction of this foo function is at address 0xf70, and the last instruction is at address 0xf7f. Well, for simplicity, I'm assuming that the size of every instruction is 1 byte. And you know that this is not, of course, true for x86 architecture being a CISC machine. So forgive me for this. Well, dear students, to call a procedure named foo, we use the call instruction followed by the name of the procedure. Since over here the main function is calling the foo function, so we say that the main function is the caller. And since this foo function is being called, so we say this is the callee. These are two important terms that I want you to remember: the caller and the callee. Main is the caller over here and foo is the callee. Well, dear students, the call instruction is very similar to a jump instruction. The only difference is that before jumping to this label over here, the first instruction after this label over here, it saves the address of the next instruction on the stack, on the top of the stack. That is, this call instruction will first save the address of the next instruction on the stack using this push rip instruction. That is, this instruction, this address will be saved on the stack, and then it will jump to the first instruction after the foo. Okay, so these instructions will start executing over here, and at the end we have this ret instruction. And this ret instruction over here is used to shift back the control of execution to its caller, and this is done by the pop rip instruction, which will pop off the return address from the top of the stack and place it inside the rip register. And this is shown pictorially over here, that we have moved back to this location. Okay, so after having a general idea about the working of this call and this ret instruction, let's see a complete example program. Well, in this illustration, I will try to describe as to how the return address is pushed on the stack by the call instruction and how it is retrieved or popped by the ret instruction. So here is the code of a program named proc1.nasm having two functions, main and print msg, with main function as the caller and print MSG as the callee. Do note the use of the global directives. Well, dear students, by default, the functions you define in assembly are only visible in that source file. To make these functions visible from another object file, we use a global directive. Over here, since the main function, this main function, need to be called from a C library module. So while programming, you must declare it with the global directive so that it can be called from the C library. Making the print message function global is optional. So if you don't write this line over here, even then this program will successfully assemble and link and execute. However, if you think that this print message function will be called from another source file, only then declare it with global directive. And then you can call it from the other source file by first using the extern directive. Okay, let me come back to the call instruction over here. And for that, let's assume that when the program execution reaches the first instruction over here inside the main function, this is the layout of the stack with the RSP pointing to the stack top. That is the last inserted item on the stack. And remember, the stack grows from the higher addresses towards the lower addresses. Okay, so let's suppose that the RIP register contains the address of this call instruction right now. The call instruction will first push the contents of RIP, and once this will start its execution, the RIP will be pointing to the next instruction in sequence. So the address of this move instruction will be placed on the stack. So RSP will be moved down and this return address will be pushed on the stack. So the return address is now at the top of the stack. After this, the control will be transferred to the first instruction after this called function, that is the first instruction of move like this. The control will shift over here and the function print message will execute its instructions one after another, and these are actually placing the arguments inside different registers and then making the write system call to display the string PUCIT, this message on the screen. And after that this ret instruction will execute. Okay, the ret instruction is going to shift the control of execution back to its caller over here by doing a pop rip instruction. So this will pop off 8 bytes value, which is the return address from the top of the stack, place it inside the RIP register, that is the instruction pointer, and the control will fall back to the next instruction in sequence over here. You see, this will be popped, the stack is shrinking now, RSP has moved back. Now the RIP contains the address of this instruction, so the control has moved over here. Okay, dear students, before we move on to the terminal and execute this program step by step in GDB, let me touch upon two important concepts. The first is about the stack alignment. Well, the stack pointer RSP should be kept 16 byte aligned upon entry to a function. That is, the hex value of RSP should end in a 0. Once we entered in a function, the RSP should have the least significant how many bits? Just 4 bits with 0. Soon I will show you this on terminal. So this is known as stack alignment. If the stack is not aligned, once you enter in a function, your program may crash. The second concept is about the near and the far procedure. if the caller and the callee, that is the main and the print message function, both lies in the same code section, the callee is a near procedure and the call instruction pushes only the IP on the stack, which we have seen over here. However, for far procedure, the call instruction will push both IP and the code segment register contents on the stack. So we will be dealing with the near calls in this course. So just a difference you need to remember. Okay, so let's now move on to the Linux terminal and execute this program inside GDB with PIDA. And before that, let me show you the contents of this file, proc1.nasm. So this is the same piece of code. We just have move and XOR instruction in the beginning. Then we are making a call, and this is the print message. Okay, so let me assemble it. nasm-f elf 64-g proc1.nasm. Let me link it, proc1.o. Okay, so this warning is because this linker LD expect the underscore start symbol over here, while we have used main, which is the default for GCC. So let me do GCC instead, proc1.o. So it has successfully generated the a.out. So let us load this a.out inside the GDB in quiet mode. Okay, so well, we have discussed this GDB with PIDA in the previous session, and right now our GDB is running with the PIDA plugin. And let me put a break at main function now, and let me run. So great, let me shrink it. So we have the 4 sections: the register section showing you all the registers, the code section showing you the code, the stack over here, and finally over here we have the instruction that is going to be executed next and the command prompt. Okay, so let me run it with pressing SI. Right now the instruction to be executed is this move instruction, which is moving this 64-bit value inside RAX. Note the contents of RAX. Once I execute this instruction, the contents of RAX are changed to this value. Now I'm doing XOR RAX. So the contents of RAX register will be zeroed out. Great. Now we have the call instruction. So this call instruction is going to shift the control of execution to the function named print msg, which is at this address. Note, right now we are at this address. Note the top of the stack right now. This is the next instruction after the call instruction. So this address, that is 5142, will be pushed onto the top of the stack. And after that, the control will be shifted to this address. Let me press SI. Keep a note of the contents of the top of the stack. Keep a note of the RSP register DF98, which contains the address of the top of the stack. Keep a note of the RIP register 513D, the current instruction being executed. So after I press SI, the top of the stack will be changed and this 5142 address, that is the return address, will be pushed at the top of the stack. So you see 5142. Moreover, now the top of the stack, that is the RSP, should be pointing to DF90. RSP is pointing to DF90 and RIP is now at 514E, which is the first instruction of the print message function. And these are the 4-5 instructions which are going to make the right system call. Let me press SI and keep executing these instructions. And finally we have reached this syscall instruction. This syscall instruction will execute and will print the message PUCIT on screen. And now we are at the ret instruction. Dear students, remember this is the return address where we want to return, which is at the top of the stack right now. This ret instruction will pop this address and will place it inside the RIP. RIP right now contains the address of this instruction 5169. So after I press SI again, this ret instruction will pop this address from the top of the stack and will place it inside RIP, and over here you will see the control will be shifted to the first instruction at this address. Great. 5142. So RIP now contains 5142. The stack has shrinked. And over here now we have these 3 instructions which are going to make the exit system call. To exit the program gracefully, let me press C to continue, and there we go. The program has exited normally. Let me press Q to quit, fall back onto the terminal. Okay, dear students, let me show you another example program. Cat proc2.NASM. Well, in this program, this is a minor variation of the previous program. Can anybody tell me what will be the output of this program once executed? Well, yes, the main difference lies over here. We are calling the print message function 16 times because this RCX register is initialized with hex 10, which is decimal 16. And this loop instruction implicitly decrement the contents of RCX register and will repeatedly jump onto this label repeat until RCX becomes 0. So this loop will run 16 times. So apparently it appears that the message PUCIT will be printed on screen 16 times before this code is executed and the program exits gracefully. Okay, so let me assemble it. NASM-F ELF64-G proc2.NASM, and let me link it using GCC proc2.o, and let me execute it a.out. Oops. So it appears as if our program has entered in an infinite loop. Let us load it in GDB and find out the reason. Let me load this program in GDB in quiet mode, a.out. Okay, and let me put a break at main and let me run. Okay, so here we are. Let me shrink it a bit so that we can see the registers over here as well. Well, over here we are at the start of the main function. Let me press SI. Fine. The ECX now contain 10. Where is the RCX register? So this is the RCX register which contains hex 10, that is 16. Great. Now we are going to call the print message function. So let me do SI again. We are inside the print message function. Let me continue. Let me continue. Let me continue. Right now I am on this instruction, the syscall instruction. Note the contents of RCX. It contains 10. I am on this syscall instruction. Once I execute this syscall instruction, keep a note of this RCX register. So the syscall has been executed, and right now this RCX register contains a Greek value which we don't know why this write syscall has placed over there. Anyway, after that we do a return, and now this loop instruction will execute. This loop instruction will of course decrement a number from this register RCX. A number has been decremented. We have again gone to the call print message function, and if I keep pressing this, we again come on to this syscall and keep a note that this syscall will again overwrite the contents of RCX register 163. We return, come on to the loop instruction. This loop instruction will decrement 1 from this, it will become something 162, and then this will continue executing. The RCX register will never become 0, so this loop will never terminate. So we have understood the problem, and I think we have seen this in some previous session as well. Let me quit the debugger and for the time being fall back to the slides to find out a permanent solution to this problem. Well, this is the code that caused the infinite loop. Each time the print message function is called, it further calls the write system call, and the kernel code of the write system call makes changes to the contents of RCX register. And when the control fall back over here to the caller to execute this loop instruction, the contents of RCX are not what is expected by the caller function, and therefore this loop never breaks. I hope the problem is very clear to you now. So dear students, to ensure that such problem never occur in our assembly programs, we need to have a very clear understanding regarding the scratch registers, the callee-owned registers, or the caller-saved registers, in comparison to the preserved, caller-owned, and callee-saved registers. Let us understand them. Well, dear students, in x86-64, the 9 general purpose registers RAX, RDI, RSI, RDX, RCX, R8, 9, 10, and 11 fall in this category. They are callee-owned. Callee-owned means the function which is called, that is the print message on the previous slide, is the owner of these registers. Therefore, the callee can freely use these registers, can make changes to these registers. And since RCX register is callee-owned, that's why the callee, that is the print message or the syscall instruction, has made changes in RCX. These registers are also called caller-saved. That is, the main function, that is the caller function, is responsible to save them. Therefore, if the caller wants to preserve them, the caller, that is the main function, must push them before making the function call and later pop them after the function returns. I will soon show this on the next slide. And these registers are normally used for passing arguments to function. We have all seen that RAX is used to place the ID of the syscall, and RDI, RSI, RDX, RCX, R8, and R9. These 6 registers are used to pass the 6 arguments to a function. Anyway, so this is about the caller saved registers, and let's talk about the callee saved registers as well. In x86-64, these are the 7 general purpose registers that fall in this category: RBX, RBP, RSP, R12, 13, 14, and R15. Well, they are caller owned. That is, the caller, in our case, the main function, owns them. Therefore, the callee, that is the print message function, should not freely use these registers. However, they are also callee saved. Therefore, if the callee wants to use them, that is the print message wants to use these registers, the callee itself must push them at the start of the function and pop them at the end of the function. And they are normally used for maintaining the local state of the caller that needs to be preserved across further function calls. Well, once again, this is the solution now to the last program. Well, since this RCX is callee owned, that is, the print message can make changes to this RCX register. That is why this print message as well as this syscall inside the callee can also make changes to it. And over here, in this example, we have seen that the print message is not changing RCX, however, the syscall is making change to RCX. Moreover, since RCX is caller saved, so to preserve this register, the contents of this RCX register, the caller is pushing RCX before the call instruction and popping it after the function returns. One last thing, in case of callee-saved registers, for example RBP, RSP, etc., the callee needs to push them at the start of the function over here and pop them at the end of the function. And this is quite rare, I think. Well, dear students, I hope you will load this program inside GDP with PETA to have a crystal clear understanding about the caller saved and the callee saved registers of x86-64 microprocessor. And this is very important. So do that. I am leaving this task on to you. So that is all for today's session. As far as passing arguments and returning values from functions is concerned, we have not covered it today, and we will cover that in the next session, inshallah. I hope this session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.